Hey, today we're looking at graphing half-lives. So the image here that we're starting with, this is the image. Here we have a whole bunch of radioactive samples. You can see that after whatever time length it takes for half of them to decay, the half-life of the sample, half of them will be decayed. After the second length of that time, half of the remaining radioactive isotopes will decay, and so on and so forth. Take a good look at this graph. Every graph we make is going to have the same exact nice even slope to it, that first order reaction. So if you ever do a half-life graph and you end up with a straight line, that should be a really good indication that you did something wrong. Something's afoot, something's amiss. Go back and check it out. You should always have this same exact shape. What we're going to work on is making sure that we have our axes properly labeled and written up, so it's not just one half, and quarter, and our y-axis with the time on here as well. We're going to make sure we put in the proper time depending on the problem that we have. But the overall shape of the graph should always have this nice smooth curve to it. So first step, whenever you're given a problem and you have to graph it, first step, just like it was when we were solving these problems, is to build a data table for the problem. So here we are, we're working with the radioactive potassium-40 isotope, which decays to argon-40 with a half-life of 1.2 times 10 to the 9, that's billion, so 1.2 billion years. A sample of K40 is found to have 32 million radioactive atoms. How many of these atoms will be left after 6 billion years? And then they want us to graph this data. So like we took a look at yesterday, the first step is going to be building a data table. So at half-life 0, we have time 0, we have our initial amount, our 32 million atoms of K40. After one half-life, 1.2 times 10 to the 9th years will have passed, and we'll be down to about 16 million atoms. After a second half-life, 2.4 billion years will have passed, and we'll be down to 8 million atoms. After a third half-life, we'll be down to 3.6 billion years and 4 million atoms. Fourth half-life, we get up to 4.8 billion years and 2 million atoms. And after a fifth half-life, we get to 6 billion years and we're down to just 1 million atoms. So we've answered the question already. How many of these atoms will be left after 6 billion years? Well, we have 1 million atoms remaining. But the second step here is to graph the data, and that's what we're going to work on today. So first step is we want to label and address our y-axis. So there's your y-axis, there's your x. Start with 0 at the bottom. So there's that, and your maximum amount, your initial amount, which was 32 million atoms on top. Next, we want to find a number that 32 will be divided by pretty evenly. I went ahead and chose 4. 32 divides by 4 nice and easily. Generally when we're doing this, I wouldn't think you'd ever go above 10. 4, 5, 6, those are all really good numbers. So hopefully the number that you're working with, your maximum or starting value, divides pretty evenly by 4, 5, or 6. Those are probably going to be the most common numbers you use. So 32 divided by 4 is 8. So I'll go up from 0 is 8 million. Plus another 8 is 16 million. Plus another 8, I get to my 24 million, and plus one more 8 would get me to my 32 million. Finally then, make sure we add a label with our appropriate units. So we're looking at our amount remaining, and right now we're counting atoms. A lot of times we might count grams, but for this particular problem, we're counting atoms. Special quick note here on even intervals. This is the biggest mistake, and it's the most often mistake made during graphing half-lives. People just look at their data column and they just plot the numbers that they see. The problem with that is they don't have equal intervals. So you can see that here. We start by going down by 16. This interval here is the same exact size. See, it's just as much space on the graph, but now we're only going down by 8. And once again, we have the same exact space on the graph, but it's only worth 4. So how do we go from 16 million, to 8 million, to 4 million, yet it's still the same space on the graph? That's not right. That's not good. The graph that we made went down by 8 million, by 8 million again, by 8 million again, and by 8 million again. So this graph is good, this graph is bad, this is awful, it's going to ruin the whole shape. You're not going to get that nice smooth curve we talked about. And as I mentioned, that's the biggest mistake. So watch out for that. Double check. Don't let your intervals be anything but equal. If you choose 8 to go by 8. Don't go by 8 and 16 and 4 and 2. Don't make that mistake. It's made way too often. All right, next up, we're looking at our x-axis. Now, this should always be your time. That's going to be your independent variable. And this one should be a lot easier to do. The time is going to be a half-life, which should always be an even interval. So if we look back at our data, this time you're okay to just plot your data. We always went up by 1.2 billion years. That's an even interval. So here I can just plot my even interval. 1.2 billion, 2.4 billion, 3.6 billion, so on and so forth, up to our 6 billion. And that comes just straight from the data. Add your appropriate label with your units. Again, this time we're working with years. Could be working with seconds. Could be working with minutes. Could be working with hours. Watch that. Make sure you give it an appropriate amount of units. Step 4 then, we're going to plot our points now that we have our axes addressed. So at time equaled 0, I had 32 million atoms. At time equaled 1.2 billion, I was already down to 16 times 10 to the 6, 16 million atoms. So we already covered half the y-axis, and we've only covered the first little point on, or first data point on the x-axis. But that's okay. That's the type of graph that we're making. Next, we went from 16 to 8, but we only got to 2.4 billion years. And again, that's absolutely fine. That's actually exactly what we're looking for in this type of graph. Our next data point was at 4 million atoms, which is, and here you can kind of eyeball it. We don't have a data point made for it or an interval in the graph, and that's fine. That's okay. It's going to happen. We can kind of eyeball it and say 4 should be halfway between 8 and 0. That's roughly here. We'll move it out, and that was at 3.6 billion years. Next data point was 2. So now we're at, basically, we're kind of eyeballing it here, and a quarter of the way down from 8. Or if you know roughly where you put your 4, halfway between that 4 and 0 is the next half-life. So there's that one. And then finally, we went all the way down to 1 million atoms. And again, that's going to be 1/8 of this, or again, that's tough to eyeball, maybe 1/2 of where you were on the last one. So there's our data points. Next thing, this is going to take a little habit forming. It's a good habit to form, though. Circle your data points. When you get to higher level labs, they insist that you do this. The reason being that when you go ahead and plot your line through it, a lot of times your data points, your actual data points, get covered up by the line. You can't see them. So circle them. They stand out a lot better. So go ahead and build that habit now. There's my circled data points. And then finally, I'm going to connect my dots and make that nice, smooth curve that we're looking for. Don't worry about a line of best fit. If you've done your axes correctly, you're always going to have that smooth line that we're looking for. And again, if you don't, if you have a straight line, it should be an indication that you did something wrong. So go back, look at what you did wrong. This is a good looking graph. Just one thing missing, the biggest thing, the easiest point for you to get, but also the easiest point for me to take. Really super easy. Make sure you put a title on your graph. Doesn't have to be anything special. You can just write decay of, and whatever we're looking at. In this particular example, we're looking at the decay of potassium 40. So decay of K40. There it is. Great looking graph. All right. Good job, guys. We'll see you tomorrow.